How do I check the audio? I figured like the YouTube is the best way to check. If it's showing up on the stream, it is.
Okay. Well, we're also, I think you want the audio from the microphone. Let me make sure that the microphone is actually.
Let me just quickly share this link real quick.
Speakers are actually on mute, so I don't know if it's actually. I don't know if it's going to come out there. But, do you want me to get on YouTube and my phone and see?
Yeah, but you're gonna have to need the link.
Oh, okay.
Copy streaming link. There we go.
You can just chat me?
Oh yeah. What? I thought it was copied on the clipboard. Copy streaming link. Streaming link has been copied to your clipboard.
Oh. Oh, were you hitting that button or this button?
This one. I was. Tell me what.
I'm opening it now. It is open.
Oh, can you hear me?
Yeah.
Test. Hello.
There's a little bit of delay.
It's in the device, yeah.
Yep.
Perfect.
Oh, can you hear me?
Yeah.
That's actually pretty good.
Test. Hello.
There's about a 5 second, 6 second delay, but.
Perfect. Oh, can you hear me?
All right, so that's working. Do you want to make sure you don't have any audio coming out of Peter, do you?
I will, because when George and everybody talk.
Yeah. Let me check to make sure it's coming out. Peter, do you?
No. Wait, if you close it, will the streaming stop? Are you streaming?
Right now?
Yeah.
Should we still on my phone? Right now?
Yeah. Are you streaming?
Yeah, there's feedback. Yeah.
Are you still streaming? I closed YouTube.
Let's wait till it's feedback. Let's wait till it. How was you just saying it's still streaming?
How about now?
Yeah.
Still streaming. How about now?
There you go. All right, so this
Hi, Mom.
should work. It's just you have the link.
Yeah.
So that's
Oh, somebody just logged.
That was me.
somebody
That was me
joined
just
the meeting?
testing the thing. It might log in.
Okay, so where is my meeting? Shoot, this is so much to do.
All right, this should be good to go.
I'm gonna ask you for one more favor.
Sure.
I don't have any water.
You have any water? Do you have a water bottle or something to grab?
I just checked my place. It's not there. I don't.
So I'm gonna bring you. I'll figure it out.
Come on, you can just pick it up on
Yeah.
the way.
Well, no, I think they might be going to make up for donuts from this. Okay. All right. So I'm gonna go back to the lab. Grab some water.
Okay. Thank you.
Oh, she's getting it.
How do I? Hey, Anthony, do we have like a wireless mouse? In
Yeah. I have a
You're gonna love it.
Hey, George, I see you're already on. Can you hear me? Looks like George is already on.
Hi, Deeksha. Can you hear me now?
Yes, George, I can hear you.
Hi, Deeksha. Can you hear me now?
Yes, George, I can hear
George,
you.
we can hear you. We can also, I can also see you.
Can you hear me now?
Yes, George, I can hear you.
We can hear you. We can also, I can also see you.
Can you hear me now?
Yes, George, I can hear you.
We can hear you. We can also, I can also see you. This is just bad. It's George. What I said. It's just bad. It's George. I know he's not.
Hey, George.
He can't.
Oh, you can see us?
I can see.
Hey, George. What do you want me to pull us up?
Oh.
Oh, you can see us?
Oh.
You can hear? Yes, we will make sure we get it back. You can hear?
My life is on there.
Feel like okay.
Hi, George. I'm going to try and mute you and see if the echo stops. Yeah, okay. So I'll definitely unmute you, George, when it's time for the Q&A part. I did. It's like almost. Why does it keep saying that, Anthony? I am the host. In the back, Jackie. Hi, Dr. Sanford. Good, how are you? Thanks for making me again.
Not seeing you. But it was nice seeing this, you know, the core of our lab, right? You're there, good. Oh, good. I'm glad you're here. How are things going?
Oh, Brooke is on.
Hi. Oh,
Wait,
I
one
can't hear
second,
you,
George.
George.
There you go.
Brooke, can you hear me now?
I can. How are you?
Good, thanks.
Yesterday was your birthday, wasn't it?
It was.
Happy
birthday.
birthday, George.
I'm not getting any younger.
Well, you don't look it. Like, you definitely don't look any different than I last saw you.
Oh, well, thank you. I don't know about that, but I'll take it.
Happy birthday, George.
Thank you very much.
Brooke, how are the kids doing?
Okay. We have been puke and fever free
Oh,
for 24 hours.
That's
Oh.
amazing.
that's not so
success.
long.
Oh my gosh. Oh, it was rough. Yeah. I don't know.
Just think of it this way. Soon you'll have them digitizing.
I know, right? Yeah, they make tiny mouses.
No, it's not.
Alexa was definitely helpful, so.
That's very good.
You guys know each other? We did our program. We're gonna be on the advisory board. No, you don't know. You don't realize it. Don't you think being named director of inter-college robotics, and you have 3 or 4 hiring lines, that's not pitching on the 25th. Turn off the lights.
Better? Thank you. George, Brooke, we're waiting for one committee member, Dr. Lau. As soon as he comes in, we'll start, or we'll start in like 2 minutes, and he'll join in when he gets here.
Okay, Deeksha, can you hear me?
I can, yes.
Okay. I'll stay muted during your talk.
Okay, perfect. And then during the Q&A, we can always bump up the volume of the speaker as well.
That sounds good. The sound quality is pretty good from my end. I don't know, Brooke, you were pretty clear.
Okay,
Yeah,
perfect.
sounds good here too.
Okay, great. Just so you know, my parents are joining via the same medium as you guys.
Yay!
So the name that you see up there is my sister's name, and I think my dad and my sister are both logged on with the same username.
Awesome.
Very good.
Here's Dr. Tangora. It's up to him. If he wants to start without Dr. Lau, we'll just start. Do you both have a cutoff time curfew-ish?
I'm good.
Yeah, I should be fine. I think we'll go a couple of hours probably. Is that my guess for your talk and then discussion?
About, yeah,
All the paperwork is done?
yes.
Everything?
Yeah, today.
I'm just checking until you're satisfied, whatever we say we have the mechanical engineering division. Usually, yeah, you, as long as you. Professor Szymanski said we're good.
Okay.
Hi George, hi Brooke. Oh no, you're the man of the hour. Wonderful. Hi guys. Hey Brooke, how are the girls?
Well, Ada's doing well. She's good. So fingers crossed.
Good. Well, thanks for being able to call and thank you too, George. So we are now at fully staffed, and I'm going to do the bio. Thanks so much for being around and for doing this research with us.
No problem.
When you say you're ready, I will introduce you. All right, great. Alan, do you want to check anything? You good? Thank you all for being here. And first, thank you to the committee for being part of this, and for George and Brooke in particular for being part of this from the very beginning and actually getting this research moving forward. So I'm going to give a little bio about Deeksha, give her background, and obviously she's going to be defending the scientific portion of it. But it has been a privilege to have been part of your development these past 6+ years. She had her undergraduate degree was from Cal Poly Pomona in electrical engineering, and then she joined our lab, maybe I'll say over 7 years ago, into our lab, and immediately started doing mechanical engineering and biology. So I think it's difficult enough when you shift your PhD and you introduce one new discipline. She shifted from circuit design into 2 new disciplines and has done really well in both areas. She'll talk about the science, and I'm going to talk about some of the other things. A few things that were very important for us as a department were her work in our courses and education. So she really revamped, was instrumental in revamping our MDM 435 courses, which are designed. And with that, she established some really wonderful partnerships with Mike and Marai at the Academy of Natural Science, but also the Franklin Institute and the Aquarium. And that's something that has been with us for now 5 or 6 years, and the new professors who are taking over are leveraging that, and that's become a permanent part of our curriculum that is really critical, I think, in the development of the students, and she really led the charge of that. And for that as well, developed surveying tools, as well as wrote some educational papers, so she has an entire body of work that could stand on itself in education. She won't talk about that today, but it was something that she just also did, which I think was really important. Really means that through this academic process, you were able to pick everything that you would want from a student, but usually we're happy when people do that 60% of everything possible. So I commend you on that. In addition to that, she doesn't like to do one thing at a time. She got married, and she had a baby. And she's already a faculty member at Villanova. So this past year, while she's finishing up, she's already been working on the design program and teaching courses that has built out her own lab. So with that, we're very happy that you are closing one thing that you're doing as a PhD student, and we look forward to a long time of collaborating with you as a professor in your lab. So with that, I'm looking forward to this event.
Great. Well, thanks everybody for joining, and thank you for the introduction, Dr. Tanguera. So again, thank you for being here today. I'm super excited to share my PhD work with all of you today. It's been overwhelming, but I'm very excited to share how everything kind of comes together. So the title of my thesis, my defense, is is experimental techniques to investigate compliance of fish fin during natural swimming. And I've been working very closely with Dr. Lauder, Dr. Fulmang, who are joining us remotely, and Dr. Tingor on this research. So I'll start by giving a quick intro. It's not a defense without some technical glitches. There we go. I'm going to start by giving a quick overview of fish fins. These fins of these fish have been at the center of studies in the biology field as well as the engineering field. Understanding how fish use these fins has been used to advance knowledge about biological evolution and physiology, but also advancing bio-inspired designs for underwater vehicles. And study after study consistently has shown that these fins, who have crazy kinematics here, as you can see, for different swimming behaviors, are not rigid plates. They're not a flapping plate underwater. These are compliant, complex structures that bend under fluid loading. They change kinematics under different swimming behaviors. So while using videos like this and many kinematic analysis techniques, the body of researchers who've been working on this have a very good understanding of the kinematics of these fins, but the compliance of these fins has been not as extensively studied. But just because it's complex and difficult to interrogate has not diminished the importance of compliance. The biologists have been very interested in understanding this compliance and also compliance changes. So they've been investigating whether the fish has the capability of modulating its stiffness during natural swimming, and studies have shown that they can. Other than that, biologists have relied on some dead fish fins or bodies of dead fish to see if, how the compliance changed as, the point on the body. Engineers, again, also for advancing underwater vehicles, have looked at compliance of these fish fins. We've gone away from using rigid plates flapping on a body that's swimming to now showing, using compliant structures like so, which were developed by Gabe Carrion from our lab, and we're now moving to compliance fins. So one fin that has gained a lot of attention in this field of work of compliance changes is the tail fin or the caudal fin of the fish. And I'll be focusing on the bluegill sunfish for my thesis in the study. And the reason why this fin has gained a lot of attention is because it's one fin that consistently changes kinematics as a function of swimming speed. So biologists have shown that as the swimming speed increases, the flapping of this tail fin the flapping frequency increases. So from biology standpoint, by looking at slow swimmers that you see in the aquariums versus fast swimmers like tuna, they've hypothesized that fast swimmers are using stiffer fins. And if you look at it from an engineered structure, if we assume that a flapping structure is most efficient when flapping at its resonance frequency, then that resonance frequency also goes up with stiffness. So if I'm going to start flapping faster, I must also get stiffer to stay efficient, or at least keep flapping at resonance. So this has led the biologists and the engineers to hypothesize that the fish actively changes compliance of its fin as a function of swimming speed. So where are we today in terms of understanding these compliance changes? The studies done till date have either focused on models of dead fish or parts of dead fish, or they've looked at purely engineered systems like flapping foils. But no matter how these studies define swimming performance, whether it's speed, thrust, efficiency, cost of transport, one thing that's consistent throughout every study that has come out is that compliance of a fin plays a huge role in achieving that swimming performance. The recent studies have also shown that there's no one best solution for what's the optimal stiffness. It all depends on what your swimming objectives are. So if you want to go faster, do you want to be most efficient? So this has increasingly made it important to understand what is the fish doing. So the limitation currently is that either half of the results from these studies are either coming from a dead fish, which is great because we're getting the true system, we're getting the true fin with the muscles, the skin, the fin rays. It's a complete system, but unfortunately we can't execute swimming motion with those fins. With the engineered systems, any programmable motion can be executed, but we're not truly getting the real biological system. So my effort to the thesis was to close that gap. So the objective of my work was to develop and validate equipment and technique to investigate compliance changes of a fish fin during natural swimming. So we wanted to test the fish under its natural swimming behavior and see if we can investigate compliance changes. I'm going to talk about the technique that I'm proposing through my thesis now. The methodology that I'm proposing is I can apply a short duration perturbation to the fin of a fish during natural swimming and apply that perturbation while the fish is swimming at different speeds and look at the response of the fin. And I'm hypothesizing in testing the fish at different swimming speeds. So when we experimentally do this in a lab, the way we increase the swimming speed of a fish is, you can imagine a treadmill for a fish by increasing the speed of the water that's circulating in the flow tank. So as we test the fish at higher swimming speeds, the environment is changing a little bit. We're having faster flow around the fin already. So it was important for us to understand that, or it was important for the perturbation and the responses to take that into account. Also, Also, as the swimming speed is increasing, the fin is changing its behavior, right? So at half a body length per second, the fin was barely moving. But when we tested at higher speeds, we're seeing more faster and faster movement of the fin. So that was another thing that we had to keep in mind when developing this protocol. So the perturbation itself had some set criteria it had to satisfy so we could do the experiments with the fish during natural swimming. The first one was that we wanted the perturbation to be aimed at the fish. We didn't have much control. I think the biologists will attest to that. We don't have too much control over getting the fish in a particular position and then leaving it there or trusting it to stay there. So we wanted to, the device had to be aimable. We needed it to, I wanted the vortex rings to be modulable in strength. So I wanted to have fast, slow, big, small, different types of vortices. These vortex rings had to travel in different flow conditions. They had to interact with the fin for a short period of time, cause a measurable change in the deformation, and not stop the natural swimming of the fish. So we wanted the fish to come back to natural swimming. Now, when I talk about the response of the fin, how do we characterize that? When we talk about the response, we want to look at the response of the fin due to the perturbation. So any natural swimming, displacement in the fin, any movement in the fin that was due to the unperturbed state was first removed from the movement of the fin. And so that gave us the deviation of the fin from natural swimming. And the second thing was cutting off the response at the moment when the fin begins to return back to its original unperturbed position. And this was because we were interested in looking at the passive response in the fin before the fish had actively realized that I just got perturbed and probably did something, because that's something we are not going to be able to isolate or communicate with the fish. So those are the two main criteria. We're looking at the deviation in the fin from natural swimming, and we want to only look at the response before the fish actively brings the fin back to unperturbed motion. So to meet my objective of developing the technique and the equipment within those constraints that I just described for the technique, I had three main research milestones. The first one was to develop a device that could perturb the fish during natural swimming. The second milestone was to do a qualitative assessment of the compliance of the fish fin, which was done by comparing the response of the fish fin at different speeds to that of flexible foils. And the last milestone of my research was to quantify the technique and validate if by examining if I can use the technique that I'm proposing to predict a compliance change in a physical system where I know what the compliance change was. So I'll talk about that in detail as I get to that milestone. For now, I'll start with the first one. So after considering three different concepts for vortex generator design, the final design that I stuck with of generating vortex rings consisted of having pressurized water stored in a tank, which was then released through an electronic valve, released through a tube this cavity that sits underwater pushes the ball that's inside, which then pushes the water in front of it, has a sharp plate here, which gives that jet of water a roll up into two dipoles that rotate oppositely and traveling in a straight line. This design gave me control over 4 different parameters, and this was desirable because I wanted control over, my parameters. I could tune the vortex rings, but to learn how the vortex rings could be tuned, I conducted series of experiments where I examined the effect of these parameters on the resulting vortex formation, travel, size, and speed. And I also conducted experiments with the fish to make sure that the perturbations we were able to produce were adequate for the fish. So general outcomes were that the equipment was successfully able to produce vortex rings that were easily modulatable in size and speed. These vortex rings did cause measurable deformations in the fish fin without stopping the natural swimming in most of the cases. The flow of the water did not drastically affect the formation and travel of these vortex rings. It did it changed the trajectory a little bit, but the vortex generator design was flexible enough to adjust for that before running the experiments. And the flow of the water dropped the vortex speed down because this was flow coming perpendicular to the vortex travel. But again, the generator was designed to compensate for losses because of the flow speed. So overall, the outcome of the first milestone was a successful device that was able to conduct the biological experiments. Once I had the device characterized and I understood how I can control these vortex rings, my next milestone was to qualitatively assess compliance changes of the fish fin during natural swimming. So there were 2 main research questions for this milestone. The first one being, how does the caudal fin of a fish respond to a vortex perturbation, and how does this response change with swimming speed? And the second question was, how does this response of the caudal fin compare to that of a flexible foil, or different flexible foils of different flexural rigidities, and what does that comparison tell me about the compliance of the fish fin? To answer the first question, I conducted experiments with 2 different fish. Both times the perturbation was kept at a similar size and speed, so we could be confident that it's a similar impact on the fin. And to compare the response of the fins from those biological studies, I conducted experiments with flexible foils in stationary water, so no flow, as well as each foil was tested at their respective self-propellancy. When looking at the videos for the fish, 3 points. So first, all the videos where the fish did not return to natural swimming were removed from the analysis because we only wanted to include the ones where there was a passive deflection and a return to natural swimming. And then, as I discussed before, I computed the deviation of the fin from natural swimming. And for each video, 3 different points were tracked: the peduncle, the point where the vortex made the impact, which was where the center of the vortex aligned with the fin, as well as the tip of the fin. And then all the movement of the peduncle was also removed so that we were looking at these deflections in the 2 points from the peduncle. So we could assume the body up until the peduncle was kind of fixed, much like a shaft, similar to our foil. For the foil experiments, the foils were tracked similarly. The 2 points that were tracked were the point where the vortex made the impact, as well as the tip of the foil. So the main outcomes of this milestone. When perturbing the fish at different swimming speeds, we saw the caudal fin get deflected, in some cases getting deformed and cupping around the vortex, and then the fin returning to natural swimming. And we saw that behavior at all the swimming speeds that we tested. Regardless of how fast the fin deformed, we saw a decrease in the max deflection. So again, I'm only looking at displacements up until the fin returns back to the unperturbed movement, right? So, and that's where we're cutting off and assuming that the fish is now actively controlling the movement of the fin. So when I compare those max deflections, we see a consistent decrease in the deflection with an increase in swimming speed. I also decided to look at, instead of, in a lot of the experiments with the fish, the time at which the max deflection reached before the fin returned to natural swimming was around anywhere between 20 to 100 milliseconds. So I decided to look at the responses just at the 20 and 40 millisecond mark to see if, if the 100 millisecond was not the cutoff for the passive response, what's happening at even shorter periods of time. And what I saw was even during the 20 millisecond period, for both fish, we see a decrease in the deflection when the fish transitions from not using its caudal fin to now flapping its caudal fin. The one place where we didn't see a significant change was when the fish had already started using the fin and the swimming speed increased. But we did not have enough trials that were consistent in the location of impact and the movement of the fin, so we weren't able to compare it for multiple trials. And we saw a similar trend for the fish when we cut off the response at 40 minutes. Now, when I tested the flexible foils, the compliant foil also kind of cupped and bent around the impact point. It buckled. There was significant deformation during impact. And you can see that the tip doesn't quite behave as the same way as that point of impact does, right? It's kind of even moving in a different direction than the other points on the foil. While the stiffer foil showed minimal deformation at the point of impact, and the tip began to move in the same direction of the perturbation almost at the same time as the point of impact. So this difference between the way a tip behaves and the way the point of impact on a foil behaves, it can tell us something about the compliance of the fin. So if I didn't know which fin was compliant and which fin was stiffer, I can look at how these 2 points are moving relative to each other and make some conclusion about that must have been a more compliant fin than this one. We also saw, as expected, that an increase in the flexural rigidity of the foil decreased the deflection and decreased the rate at which it was deflecting. But we also saw that the increase in the flow around the foil also contributed to decreasing the deflection of the foil. So by comparing these shapes, so we saw that the caudal fin at the low swimming speed behaved similar to the compliant foil when getting perturbed by a similar perturbation. So we see that local deformation at the point of impact, and we see that the tip and the point of impact don't quite behave the same way as they did in the stiffer foil. And we saw that the caudal fin at the higher swimming speeds had minimal deformation at the point of impact, much like the stiffer foil, but also the deviation, as you can see here in the red and the blue from natural swimming motion, was very similar, happening at similar times, happening at similar rates. So those points are now starting to move closer to, similarly to each other, much like what we saw with the rigid foil. So the comparison of the caudal fin at low swimming speeds and foil and a compliant foil, and comparing the caudal fin at high swimming speed and a rigid foil suggests an active stiffening as a function of swimming speed. So as the swimming speed got higher, the fin starts to behave more and more like a rigid foil. So that brings me to my last milestone. So one limitation of conducting the experiments with the fish was the caudal fin is a complex structure. This was the first time anyone had done such perturbation studies. So by looking at the response of the fin, it bends, it deforms, it rotates, it rolls, and we didn't know what to predict from the fin, right? So we're still hypothesizing that the fin is getting stiffer at higher swimming speeds, but I couldn't predict because I didn't have a mathematical equation where I could put in a force signal and predict what the output would be, because that force of the vortex ring on a flexible structure is also an unknown. So there's really only one study that has looked at impact of vortex rings, and they haven't done it on flexible foils. So there were two unknowns in my equation. The only authentic measurement that was true was the measurement I was getting live from the experiment. So to quantifiably validate this experiment, I decided to use my technique that I'm proposing, apply it to a system that I was confidently able to model mathematically so that I could predict how this system would respond and then compare it to what I'm actually seeing in the experiment. So the objective of my last milestone was to predict the known compliance of a system using this perturbation technique. The three things that we needed for this were an estimate of the force of impact. We needed a physical model, which was serving as the approximation of a fin for us. So we needed this system to be able to get perturbed and then move in response to that perturbation. We needed a mathematical representation that was an approximation of the physical system, so we could predict the response and compare it to what we're seeing experimentally. So the estimate of the vortex ring was determined, or I'm sorry, the force of the vortex ring was estimated by firing the vortex ring at a rigid plate that was attached to a force sensor, so we get a direct measurement of what that force is. The physical model that was built to conduct these experiments consisted of a rigid plate attached to a compliant foil, and this foil acted like a spring and gave the plate the freedom to move in response to the perturbation. And the response of the plate was characterized by looking at the displacement in the tip of the plate. This model was mathematically approximated as a lumped parameter mass spring damper system. The response of this mathematical model was predicted by convolving this estimate of the force with the impulse response of this function, which is a function of the mass, the damping, and the stiffness of the system. And these are the system parameters. The response was predicted and calculated using a computer software, and these two responses were then compared to identify the parameters of the system. So these were initially estimated, and then a close match between the two gave me improved estimates of the parameters. So the two main research questions for this final milestone were, what is the force of impact of the vortex ring, and how does it relate to the vortex characteristic? And how well can the perturbation technique the estimate of the vortex force, and the measured response determine stiffness change in a system? So for that first question, I conducted experiments with a rigid plate attached to a force sensor. I used vortex ring traveling at 5 different speeds. At each speed, 5 different trials were conducted. They were averaged, and the average was compared. For the second question, similar perturbation studies using the vortex rings from the previous study were used to perturb the physical system that I had built. And the stiffness of this physical system was changed by swapping out the foils on this connection. So each time the stiffness changed, I physically changed the foil attachment here. And the displacement of the plate was measured again. So as expected, the outcomes for the first question about what the vortex force is, we expected that as the vortex got faster, the momentum increased. So we would expect a stronger vortex, and we saw that. So the peak force increased with vortex speed, but so did the duration of the impact. From the second question, we saw that the physical system responded in a way that was characteristic of a second order system. We saw these sinusoidal oscillations that damped and decayed over time. We also saw that as the stiffness of my physical system increased by 3.5 times, I did not see any change in the exponential decay. I saw an increase in the damped frequencies, the damped oscillations, frequency of the damped oscillations. And as expected, I saw a decrease in the deflection, the max deflection, and a decrease in the rate of that deflection. So my next task was to now develop the mathematical lumped parameter model. I'm going to skip the details on developing this because I'm happy to discuss this more during the Q&A. But I developed a lumped parameter mass spring damper model that related this external force being applied by the vortex to the parameters of the system. And this is where I'm changing the value for it. It's this K value where I want to change it and then see how the response changes with the change in stiffness. And the simulated response from this model was computed by convolving the estimate of the force, which again was measured, and the impulse response function. So the outcomes, we modeled this as a second order system, so it behaved like one. But the 4 characteristics of the response, as we expected, were as the stiffness in my mathematical model increased, I saw no changes in the exponential decay. I saw an increase in the damped frequency of oscillations, or frequency of the damped oscillations. I saw a decrease in the max deflection, and I saw a decrease in the rate at which that deflection, the plate deflected from unperturbed to the max T. So seeing these similarities as a function, so both systems, my experimental and my measured system, showed similar sensitivities to a change in stiffness. And this was at the core of validating this technique. I knew what to expect because of the mathematical model. I knew what to expect. I knew how much the response would change. And seeing similar changes in the response of the experimental system was the first step to validating that this technique could actually work, or it does work. So this is a quick summary I want to show you. The 4 different things that I've kind of talked about are the max deflection, the frequency of the damped oscillations, the rate of decay, and the rate of deflection from unperturbed motion to the max peak. And what we see was 3 out of these 4 metrics, the changes in the simulated and the measured response were very similar and in many cases the same. The one place where we saw slight disagreement between the measured and the simulated responses was in the frequency of damped oscillations. Now, when I think back about the fish, this metric doesn't quite matter because we're never going to have damped oscillations in a fin because a fin is an active system, right? So we're never going to have, and these are all passive systems. But I wanted to validate if my assumption of the model and my estimates and my force, where have I underestimated or overestimated something? So I decided to look at the actual responses and not just the relative changes in the responses. And what I quickly noticed was for the rigid foil, for the rigid system, the experimental, which is in blue, and the simulated, which is in green, were very similar to each other. So there was very less deviation in those. And what you see in the black is a model fit, which was the best fit that minimized the sum of squared difference between the measured and the simulated response. The one place where I clearly saw, something I clearly saw was that I had underestimated my compliance for the compliant foil. Okay, so by looking at the green and the red here, what I noticed was the exponential decay of these peaks was very similar. So just to kind of begin my initial estimate and start playing around with the numbers, I concluded that I had a good guess for D over 2m because the exponential decay was the same. So my first guess was I probably underestimated the K value. And when I did the parameter fit by minimizing sum of square difference, I did notice that I had estimated the stiffness to be 0.024, while I'd underestimated by close to 40%. It was interesting. Again, going back to the fish, this may not matter so much, but when it comes to validating the system I used to perturb and compare, this was important to know that for the more compliant system, I tended to underestimate what the stiffness was. Another source of error could also be that the estimates were determined by doing static point loading in air versus these foils actually bending in water. And the more compliant you get, the more deformations and the more you start deviating from a beam bending equation or behavior. So this was key information for improving these models as time goes by. So I've taken you into the weeds. I'm going to try and bring this back out. I started by wanting to apply a force to a fish, a fin, or a structure, anything. But what I wanted was a force. I decided to use a vortex ring to apply that force to the fish fin, which then can be fired at a rigid plate with a sensor on it, and that experimental vortex ring turns into a force signal. This experimental vortex ring then perturbs a physical model, while the signal becomes the input for a mathematical model. So now I have 2 different tracks of response I'm going to get. I'm going to get an experimental response, I'm going to get a predicted response, and seeing similar sensitivities to a change in stiffness in the mathematical and experimental model was promising. It showed that this proposed technique of applying a known force and looking at just the deformation can give us an estimate of a compliance change in the system. But again, I'm going to go back to my main stakeholder here, which is the fish. I'm never going to have these kind of decays. So for the validation of the technique for biological experiments, I decided to get rid of those two parameters, the frequency of oscillations as well as the decay. And I just looked at the changes in the response up until that first peak and saw that even with that constraint, I saw changes in those two metrics as I would have expected from a system that got 3.5 times stiffer. So where does this all kind of fit together? Again, the mathematical model, under the assumption that this is the model I'm starting with and saying this is a good approximation for the response up until that first peak, I knew what to expect from a system that gets 3.5 times stiffer. This was validated by perturbing a physical system that was a close approximation of this, and we saw similar changes. And what was even more promising was that when I compared the response of the fish at 3 different swimming speeds, as we go from red to blue to green, we see the swimming speed increasing, and we see a similar trend in that response as we saw in the simulated system as well as the experimental, the physical approximation of it. So this was promising. This was all good news. So I started here. I had 3 main milestones. I'm very happy with the outcomes. For my first milestone, I have a device that can produce controlled perturbations. They're consistent. They're adequate for the biological experiments. It's compact in size, and it is scalable. At the end of this research, I have a good understanding of if I wanted to scale the vortex generator up or down, so for bigger fins and stronger systems or tinier fins and more delicate systems, I have an understanding of how to do that. Through my second milestone, I saw solid evidence pointing towards a stiffer fin and higher swimming speed. And from my third milestone, I was able to validate the use of the response of the system till the first peak and to conclude something about a compliance change. But being that we're all scientists here, I kind of want to talk about some of the limitations here. The one thing that I wasn't able to address was the isolating the effect of flow from stiffness. So we did see the flow affect stiffness, but this wasn't investigated further with the fish just because we know very little about the model. So I think more experiments with the flexible foils are going to be important here to really understand how the flow is going to affect the response and the time dependence here, right? So what I mean by that is we see these systems, the fish fins respond or deflect for anywhere from 20 to 100 milliseconds. So what if the caudal fin got deflected and it kept deflecting for 100 milliseconds, but another fin on the fish had already responded to that perturbation at a 40 millisecond mark? Then we can't be sure that that 100 millisecond is still a passive response. So what I wanted to do was go just one step further and say, what would happen if I took the response of my simulated system and instead of cutting it off at the peak magnitude, I started cutting it off much earlier, like at 100 or a 60 or a 40 or a 20 minutes. So with the given system that I had, and with the way the analysis was done for this entire research, I was constrained by the tracking methodologies that I was using. So the smallest displacement I could measure was it was less than half a degree, so 0.4 degrees. So if I took the response of my simulated system from the time it reaches half a degree, which tells me that this is where I'm going to be able to visibly track it, to 100, 60, 40, and 20 milliseconds, I didn't see a measurable response, a change in the responses in those short time windows. So I thought, what happens if I make the system lighter? And as I made the system 1/8 of its original mass, I saw that I was able to predict the change in the stiffness as quickly as 100 milliseconds, but not quite there at 60 or 20. As I kept making the system lighter, the predictions got better, right? So I was able to kind of predict it right here at 60 milliseconds as well. But as I kept making the system even lighter, that validation began to drop again. So we see this little sweet spot, and then the technique kind of begins to fail. Not fail, but not work. So this could be because of many factors. Could be the force estimate, could be that this is at these stiffness and masses, the model that I assumed is not really a good model. I also said, what if at that mass where it was starting to work really well, what if it was a larger change in stiffness? And again, we see like at some changes, we're getting good measurable responses, but again, you start to see kind of decline in being able to predict those responses. I also looked at what would happen if I applied a stronger perturbation. And of course, as expected, the magnitude went up linearly, but at the same time, so the rate of change did increase, but to get that much sensitivity here, we would need a much, much stronger perturbation for this system that I had built, which I wasn't able to kind of experimentally test. But the one thing that can really help this is improved tracking. We are seeing similar trends, even as quickly as 20 milliseconds, but we need better tracking that isn't bounded by human vision limitations. So some kind of automated tracking or faster sampling, better quality videos. And I believe that's something that we can do with the newer cameras that we have. Some of the major research areas that have branched out of this are in experiments in fluids. I'm currently collaborating with Dr. Crane at Penn State. He was the one study that I found that had looked at direct force of vortex on a rigid plate. We're working on some publications on the interaction of the vortex rings with flexible foils. But this technique, the equipment, the outcomes of this thesis continue to contribute to understanding fish locomotion. So not just looking at compliance by looking at passive responses, but this device can provide perturbations to a fish fin during natural swimming and see how actively multiple fins respond. And just my training and my experience of working with biologists consistently throughout my research has opened up, has helped me formulate two main research areas in education research, one for the undergraduate engineering education and one for K through 12, which is something I work very closely with Mike regarding. So these are some of the work that I shared through publications and presentations related to the fish. And I'm currently actively working on a paper with Dr. Crane that will look at where we'll publish the results from the interaction of vortex rings with flexible foils. And this is my total list of publications and presentations, including my educational work. I recently submitted my first journal publication for the educational research work as well, which is formally under review right now. At this point, just want to acknowledge a few people. I want to thank National Science Foundation and Office of Naval Research for all their generous funding. I want to thank the Mechanical Engineering Department here at Drexel for all the support that they've given me. I want to extend many, many, many thanks to my committee who have been very supportive in answering my sporadic emails and just have given me the most quality support that I could ever imagine. I want to thank Dr. Tangora, who took a chance on me 9 years ago and thought I could do it. I want to thank everybody from LBSA, current and past members, especially the group sitting here today. Thank you for all the time you guys have spent watching my presentations over and over again, but also all the superhero conversations we've had to take my mind off some of the stressful work. And I want to thank the main pillars of my support, my family, and the two dudes who keep me going every day. At this point, I will take questions.
I'm amazed after our multi-hour committee meetings that you use this to make sure you finished in time constraints that Alan had.
How well did I do?
Yeah, let's defer to Professor Lau so he can, if people don't mind, Professor Lau has to leave. So, unless you want to let the students go, whatever you feel, whatever you prefer.
So this is a question that I asked you before. I'll ask it again to see if maybe you didn't later. Talked about one of the major limitations being it's hard to draw out what are effects due to what is the result of which. I was wondering if you had given any thoughts of how you might be able to separate out the effects of specifically the flow around the fin, and what that might be contributing, so that you can specifically isolate the effects that you're looking at.
Yeah, definitely. And I think the way to do that is to do more experiments with the flexible foils at different flow speeds, right? So currently the experiments we did were to do that qualitative comparison, right? So we only looked at 2 foils that were 30 times stiffer than each other, and each foil was only tested in 0 flow and at its self-propelling speed. But I think we need data on how the foil responds at the speeds in between, right? So that we can develop a model that says, you know, and again, it's going to be more complicated than this, but you know, if a 20% increase in flow speed causes a 20% or 10% decrease in the deflection, then going into the fish experiments, I'm going to know that if I'm going to change the flow by 10%, the fin only deflects by 10%. I'm not going to know if that was because of foil. So that could mean, again, coming from the technique, that could either mean I hit it with a stronger perturbation, so I get a larger deformation, right? And again, that has to be validated on the foil experiments. Or it could mean that, you know, I can't isolate the effect. So for me to be able to isolate it, I need to do multiple strength perturbations on flexible foils, each foil being tested at multiple flow speeds. Oh, do you have a question? Yes. I'm going to see if I actually have that with me here.
Slide on this, then we're gonna say that was fine.
No, well, so I'd shown this to my committee before, but I did have this. Yes, it definitely matters. So the 2 things that I did notice from the experiments was that the location where it hits the fin and the movement of the fin before it is hit makes a huge difference in the way the fin responds. So when biologists start using this technique to test compliance of fish fins, we have to bin the experiments based on where the vortex hit the fin and where the caudal fin was just before it got perturbed. So you can quickly see here that the location of impact on the 2 trials here was quite similar, but you can see how different the responses were, right? So in one case, the fin was already moving away from the perturbation hit it, while on the other one, the fin was moving towards the perturbation when the vortex hit it. So you don't see a large deflection, but what you see is that the fin just they just fought each other for a little bit. The vortex stopped the fin from kind of keep moving, and once the vortex dissipated, the fin kind of just kept moving. So it definitely matters. To see this like 7 times.
I just want to get an idea. So obviously you have to roll out a lot of trials that aren't, you have to do a significant number of experiments to get ones that achieve the same at the same time at the same point. What percentage of trials are you actually able to use?
I was able to use them all, but yes, I wasn't able to compare them all, right? For example, at this speed, although I had 2 trials where the location was consistent, I couldn't average these trials out because the movement of the fin wasn't the same. I don't remember off the top of my head what the percentage would be. Not a lot. But, you know, working with Dr. Lauder and Dr. Schultz-Mang, I still remember talking to Dr. Lauder about this and saying that we need to get consistent location. How do we do that? Like, can we time things? Can I put a program on the perturber where it will just fire at a delay? And he just constantly said, nope, we just got to do a lot of trials. We'll just do 20 trials and you're going to get to use 2. But I think that was repeatedly a conversation I had with the biologist. We actually have a biologist in the room, and yeah. Yeah. So that's a new question.
I have a question on the process of biology and engineering. It's very basic. It shows what I don't know about the field. You use the body length second as the velocity scaling parameter. And things. Is that an accepted scaling parameter in biology or fish biology?
Yes, yeah, it is.
And what range is typical for
Yes, so, yes, using body lengths per second is characteristic of how biologists are defining speeds. In this case, and tell me if I'm answering the question right, in this case, we used two different fish. They were both slightly different in body length. So one was 16.5 centimeters and one was 18.5 centimeters. So the flow of the tank was slightly different to get the fish to swim at the same swimming speed. So we didn't want to keep the flow of the water the same. We wanted to keep the swimming speed of the fish the same. So how many of its own bodies will it cross per second? Did I answer the question?
A really big tank that you do a barracuda.
Can we do barracudas? That would be a pretty big tank.
One other question. For your 6th degree of freedom force sensor, how did you calibrate that?
Let me see if I still have that one as well. So the way I collected the data was every time the vortex ring was fired, there were like 5 different trials. Each of them were aligned, time-wise of like when the vortex got fired, right? So any error in the speed of the vortex was taken into account with the vortex, with the force. The 60-degree of freedom sensor, oh, I see what you mean. Okay, so like, did I apply a known force to it? I did that in air. So the way I calibrated was attached the system to the force sensor and hung a weight from it. So I kind of knew what that force would be and see if that was, if that matched the 3 different force components that I had measured. And then took that into account when calculating the force of the vortex.
So, for your vortex experiments, when you're trying to calibrate that, did the force you measure nominally agree with what you were expecting theoretically? Because you know what your vortex is, because you're generating, so you should be able to calculate the impulse of the impact that vortex transmitting through the flow in the water. Or did you get to that level?
I didn't do like a full analysis, and again, like this, when I came across the study that was done, there's really very less out there on the actual impact, like the force imparted onto a structure by a vortex ring. And really the only study that I've looked at was the one from Penn State. So I worked with them and shared the data, and we kind of talked about it. And our force scaled the same way as they had expected it to, but even their work wasn't fully theoretical. So there was no prediction, it was really all experimental.
I think we want to return to that. I'm asking, I want you to elaborate that a little bit. But I just want to make sure Alan has a chance. I know you can read. Yep. You guys have any general audience softballs? This is your last chance to ask a hard question.
Is it scalable? Yes. For a shark? I don't know. I know very less about the shark fin's properties. It is scalable because as we speak, I am with some students from Villanova. I am developing 2 bigger perturbers to do more studies with the physical systems, right? Because those systems are much heavier than a fish fin. So we need stronger perturbations to get larger accelerations on those systems. So it is scalable. I don't know if it's scalable to a shark. It would be cool if it was. The sound, yeah, I mean, it still does make a sound, the valve does make a sound, but with the fish experiments, we haven't seen it. We haven't seen that the sound made any caused any active response from the fin, or from the fish, sooner than the vortex did. So we kind of were confident that it was okay.
So that Professor Lau can ask. Thank you guys very much for attending.
Thank you. I know that some of the non-committee members are,
Are there any friends or parents in the audience?
so I'm going to request the friends and parents to kindly leave the meeting so we can have the closed door portion with just the committee members. So, Dad. Sister.
Hey, your daddy has to call me on the phone to verify that. Thank you. Are you gonna be in the same lab? We're gonna have lunch.
All right, everybody.
This being the end of the term, multiple graduate students want to finish before the final exam starts next month. It's why I think that congratulations you on good luck.
Thank you.
I just want to ask a good clarification question.
Can I just make sure George can hear them?
By definition, the Wells most expert in this particular topic, right? I mean, yes. Now, I see that your physical model, the stiffness for compliance is obviously fixed. It does not change with time. So, in your mathematical model, you try to use an inverse method to predict what is the stiffness of a constant on time variance. The whole purpose is to apply it for other people later or the biological systems such as fish, swimming. Nobody tells the fish when the fish swims. The fish should give the compliance or stiffness of the tail constant. Right? I remember when I was little, when I tried to arm wrestle with my big brother, which was 7 years younger, I deploy my muscle with the arm so that it has one stiffness. When I arm wrestle with a much bigger, older nephew, I deploy the stiffness of my muscle on my arm so that its compliance or stiffness is different than when I arm wrestle with my 3-year-old big brother. When I try to arm wrestle with a person of my same age, and I don't want to hit him or her too bad, I will constantly shift the stiffness of my arm so that we have equal contest for a few minutes. So when the fish swims, at different stages of the swimming cycle, is very light stiffness of the fish tail is good. So how do you advise future researchers to advance that?
Absolutely. So, this original methodology of using a perturbation was actually inspired from some studies done on human joints, right? So, your elbow, your ankle, your knee. And, all these biological systems are not linear time invariant. So the one way to actually look at this, how the stiffness is also a function of the, position is to, bin the experiments based on the position of the fin and the location of impact, kind of like I discussed before, but also then looking at, if this is aligned with the body of the fish, looking at the stiffness here versus here versus here, by binning the experiments based on the location of the fin and not just the impact, is the way to go. And that's consistent with how researchers have looked at human joints, right? Like they've asked humans to hold their arm position at different angles and then perturbed it at that angle. With the fish, we can't really ask it to hold the fin at a place. But I think with the biological experiment, one way to attempt is similar to what I did was it has to be compared at a certain position, and that has to stay consistent throughout.
Okay. So I only have two more questions. Second question is, after you have done what you have done, and assuming that the results, you are satisfied with the results, if someone give you a video observation of a fish swimming, would you be able to video or images predict what is stiffness of science on the fish?
Just from a video of a fish fin swimming? I mean, no, because I think the technique I'm proposing relies on applying a load, applying a force to it, and looking at the response. Right? If I take a look at the fish fin videos that I showed before, there really isn't any knowing of. We can look at deformations, but even the most compliant bluegill sunfish fin could still bend, and even the most rigid might still bend and deform, right? So just by looking at purely just the deformation that's being caused just due to natural swimming, I'm inclined to say no. There's just too many unknowns. At least with the technique I'm proposing, we are applying a known force, looking at the deformation before the fish realizes it's been hit. So I think that's the technique I'm proposing. So for me to be able to say, that was a stiffer fin than the one from the previous video, I wanted to get perturbed for a short period of time.
My last question is relatively not difficult for people to get video images, sharks, or other fish swimming in naturally in water. And it's highly desirable that looking at those video images information, try to estimate the technical properties of the fish, science, or how strong the muscles are. Knowing what you know now, if there is an opportunity to make a proposal for research, what would you propose to do so that engineers or biologists can look at three-dimensional fish videos of a fish swimming, try to get a hold of the big stiffness of the
That's a really, really, really tough thing to do, right? Again, because of the whole active responses, right? Like, we'll see the fin responding differently at different speeds. We can compare different species, but there's really no way of consistently knowing if both the fish were using the same musculature changes, right? Were they using the same muscles? Were they startled? Were they, right? So I think just by purely looking at natural swimming videos, it's going to be challenging, again, because you have so many unknowns, right? And that's why with this technique, trying to kind of, again, bring it down to, I know the perturbation, I'm only going to look at the passive response, so that even if you were, running differently, I'm just going to push you guys just until you realize you've been pushed, because I can assume that for both the subjects, that piece of response can be comparable. But, I might use very different types of musculature to run, compared to another person. So I think, look, that's why the technique I proposed. Known perturbation, passive response. Of course, no, thank you. Dr. I'm so sorry, but Dr. Before you leave, I have the forms if you can sign them. Sorry? Okay. I don't want you to be late.
If we open up, is it okay with you to just ask George and Brooke directly?
George.
Hello?
Can you hear me?
I can hear you, but it looks like Deeksha's muted.
Okay. Oh, yes.
I'm
No.
sorry. Can you hear me now?
Yes.
Okay, perfect.
Has George not been able to hear the whole talk?
Oh, no,
Start
no,
again?
no, George, I wasn't muted. You know, he would have said something.
No, just this last 5 seconds.
Can you all hear them?
What?
Can you all hear them?
Not well, but if you prompt them, if they would like any questions, and then you can say it more out loud
Okay.
to us, then.
Yeah, so George Brooke, the floor is yours.
Brooke, feel free to go first if you'd like.
Okay, so great job, Deeksha. I was very happy with the way you tied everything together, and I think you have a phenomenal body of work here, and I'm excited to see that it's as far as it is, and it looks like you've got a lot of stuff here that's not too far from publication either, so congratulations. That's very good.
Thank you.
So I noticed something, and I wanted to ask you to explore it a little bit. You talked about in your testing the compliant non-bluegill, so the 2 different mechanical fins, the compliant fin and the stiff fin. And you noticed that when the compliant fin was perturbed, it sort of bowed in the middle, and that you didn't really see the tip deflection there. So it was more like it was just sort of catching the vortex, right? And then with the stiffer fin, you saw whole lot more tip movement because it was moving as one non-bending surface, right? So you were getting a lot more tip deflection with the perturbation. And what was interesting to me was that you had a combination of both of those factors when you actually looked at the bluegill fin. And so that suggests that that's more of a factor of that you have a variable compliance along the length of the bluegill fin. And so that maybe the tip is acting in a different way than is perhaps the mid body of the fin. And I wondered if you could think about for a second what that would mean in terms of your data and how how do you rationalize the sort of what you see as an effective perturbation of the bluegill sunfish tail visually, knowing what you know about the 2 different stiffness fins and those different reactions?
Okay, so just let me quickly repeat the question, just so I understand it. So the first part was kind of think about, because of seeing a combination of deformation at the point of impact and a deflection in the tip that we see in the fin, does that hint towards a variable compliance, right? So for that first part, I think so. With the given studies, with the given experiments that we have, with the given experiments, I don't think that it sheds that much light into the variable compliance as in variation from the point of impact to the tip. So was the tip more compliant or stiffer than the center of the fin? But with the technique, and I think this was the second part of the question, but for this technique to be used to examine the variable stiffness as in varying as a function of the point on the fin. So x equals 0 is where the caudal fin meets the peduncle. X equals L is where the tip is. I think looking at the K of the fin as a function of that X is doable if we just perturbed it at different points. Because I almost feel like it's the result is the opposite. Seeing that a passive foil that has uniform stiffness shows a bending in the tip that's delayed from the deformation of the point of impact actually tells me that by looking at the same behavior in the caudal fin does not tell me of a variable stiffness, right? Because the flexible foil kind of acted similarly to the caudal fin. So those are the 2 things that immediately come to my mind. If I answered your question.
Yeah, no, I'm with you there. I think that's fine. I think the other neat thing was that in thinking about the fact that there may be a variable compliance, I think that actually helps to back up this idea of a modulation in stiffness with swim speed in the live bluegill, because you do seem to get sort of this effectively becoming more and more like that stiffer plate with your quality of deformation in the live bluegill fin versus what you were seeing in the stiffer plate versus the compliant as well.
Yeah, I agree, absolutely. And I think this is sort of in line with what Dr. Lau asked about, the stiffness isn't just, so a caudal fin that's not moving has different stiffness at different points. That's been shown, sort of, right? Like the stiffness is already varying as a function of X along the fin, but it also is varying with the stroke, the position, the position of the fin within its fin bead. And my answer to that question was, similarly to what people have done with the human joint perturbation studies, we need to be looking at the response of the fin at a given point during its stroke and comparing it at different strokes. And I know, like I said before, as many times I've told Dr. Lauder, like, well, we need to control for these. His response has been, all right, we'll just do 50 trials and you'll get 2 or 3. But I definitely agree. I think it would be very neat to look at the K as a function of X and also as a function of, I don't know, like Y, which is the position in the other axis along the anterior posterior axis. I definitely think that would be very neat. And I think the equipment and the technique is capable of doing that.
Cool. Georgia, do you have a question or?
Sure, I can ask a question if you want. I think this will probably be my only question, but I think before I do that, I'm going to just make a comment, which is that I think I learned more from Deeksha and the experiments she did than she learned from me. I thought when we started this project that the fish work would be very difficult. Brooke and I have done many experiments like this that are challenging for fish, to aim vortex rings at individual fins. But then when Deeksha and James suggested, well, let's just shoot some vortices at some flexible foils, I thought, oh, this is going to be great. It'll be so easy. Everything's controlled, no problem. And I certainly have learned that it's very, very complicated. So I feel like I've learned a lot, and a lot of the details of why and how to do these more engineering controlled experiments has been a good learning process for me. So I thank Deeksha and James also, of course, for everything I've learned in the course of this project. My one comment is really just to ask Deeksha if she could take a guess and boil everything she's done down. And just if I say a bluegill sunfish's tail, if the bluegill sunfish swims twice as fast, how much of an increase in stiffness do you think it experienced? Do you think it's twice as much, 3 times as much, 10 times as much?
It's really tough, especially because like the one thing I've gotten trained is unless you know what exactly that force was, it's really tough to say. And I think with the perturbation, with the physical model that I built, we're close though. I think we're closer to knowing what that force was. Given that, if I had to guess, and you weren't going to put me on the record, the one thing that I did notice, and this was just last week, was I went back to the fish videos when it was swimming at 0.65 and the same fish swimming at 1.5. And I tracked the vortex ring close to the interaction phase. And what I saw was that the speed and circulation and the size of the vortex were within 2% of each other. So I had good reasons now to assume that the force, I don't know what the force was, but I know it was very close to each other. And by comparing the rate of deflection and the max deflection, it turned out like if my foil had gotten about 2.2 times stiffer, I would have gotten something like that. But again, like I think I need to track it better. I had very less points to track it, but I know this isn't like a publishable result, but when I compared the deflection of the fin at 40 millisecond mark, the 20 millisecond mark, and up to the peak, which was 40 for one swimming speed and 60 for the other, I consistently see a 2.2 fold increase.
So yeah, so I think I know you're being very cautious, and I know you're just kind of not wanting to commit yourself, which is fine. That the number you gave, if the fish doubles its swimming speed, the stiffness increases by roughly a factor of 2. That would have been about what I would have thought. So
that's good news. That's
I
really
think,
news.
but of course, I'm basing my opinion on nothing.
But I think, George, we're much closer. Sorry.
I said nothing. I was going to say for about 40 or 50 years of work, it's
Yeah, true. But I think we're a lot closer to getting there than we were when I started this research. There was just so many unknowns. But I think with the upcoming the publication with the vortex rings interaction, I think we have a really good understanding of how vortex force scales with its circulation and its speed. And with I need more PIV experiments, right? We only got to do one round with the foils. But I think with more PIV data, with circulation, which plays a huge role in the force of impact, we're very close to knowing what that force even is and getting a better, it will be a one-dimensional change in the caudal fin at that one point, but it will be quantifiable. We're not too far from getting a quantifiable change.
No, I think that's fine. I think a major contribution actually that you've made is that you've figured out how to answer the question. And that's not a small accomplishment. So even if you don't have a full answer to what how the fish stiffness changes, and maybe we'll never have an answer, I think you've really shown how to go about the problem in a scientific way, which is a substantial contribution.
Thank you, George. Thank you. None of this could have been possible without you all, yours and Brooks and everybody in the Lauder lab was so immensely helpful with all those experiments.
I think that's it for me.
Thank you. Professors?
So I want to just on a board, and I think I want to echo what you said. I think that it's really impressive that you were able to take all of that work and put together, a site and well-structured presentation that really brings this all together in a way that allows for real deep thought and interaction around the work. So I think you did a really great job, and you should
Thank you.
and just sort of watching throughout your the amount of progress is substantial, and I think it's always good to reflect on that.
Thank you.
And especially in science, you know.
Thank you.
So good job. I think that I have a couple questions, but they're more in line with what I've asked you before, and I think it's more of a comment than a question. So you start your thesis and you start your talk today with this comment that lots of people have studied these problems over decades, but I feel like there's a missing piece, which is why. Why do we care? Why is this something that people are studying? And I think there are a variety of answers to that question. There could be a biological answer to that question. There could be a more engineering-centric answer to that question. But I want to know why you are studying from a big picture. Why is this interesting?
Oh,
And
just
you're
for
still
me.
doing it, and you're continuing this work in your new position. So why should you study?
So other than the advantages of, just advancing knowledge about biological evolution and physiology. Okay. So in addition to that, an engineer system, do you mean like why personally I'm interested in the field?
Well, that could be a reason, but I mean, you're not just modeling the behavior of fish fins to model the behavior of fish fins, right? You're doing it for a reason. What's the reason that you're modeling behavior?
So, academically and professionally, it is to, other than understanding, again, like the physiology and biology, and for engineers, like understanding how the stiffness should be changing to develop designs for underwater vehicles that are inspired direct from biology.
That's the piece that's missing. I think you can start your pieces and your that. Because I think that one of the things that as an audience member and as a fellow scientist, you want to play along in the audience. And it's hard since you do something at the intersection of biology and engineering. As a biologist, I'm sitting here wondering, am I supposed to be a biologist in this situation where I'm going to
I
get
see
advice
what you mean.
about the biology pieces? Or are you doing something that's not biologically related? It's more about engineering design, in which case I can wear a different, I'm not an engineer, but I can wear a different hat and help you think scientifically about how you achieve that goal. And so I think it helps your reader, your audience to know what role they're supposed to play in being a colleague and a collaborator with you and thinking about those scientific questions. Otherwise, I might ask you a bunch of questions that go down a rabbit hole that are not relevant to your work. So I think you should think about that framing when you talk to people, not because you necessarily are going to go out and do robotics work, but maybe you are. But to give that framing so that people can interact with you in the most efficient and effective way possible is helpful. And so I guess, a question I have is that something that are you going to focus on the basic science of this moving forward, or are you going to get to the point of the design element using that?
That's a good question. I haven't thought too much about it. So currently, the direction I'm kind of moving forward in is, some of those little cliffhangers that I left you all with, right? Like isolating the effect of flow from stiffness. So my short-term track includes, more studies on the foil and the physical system that I built, right? So perturbing that with stronger perturbations. And that's why with the students at Villanova, we're building like two much bigger, stronger perturbers that can really accelerate that physical system fast. So we can get that short, quick response from the models. I haven't thought about where I want to take this long term. I'm a little bit more inclined towards like that whole integrated STEM education for kids. Which has been derived from this, right? Even through the undergraduate and research experience that I'm doing at Villanova, it's more about
having that big picture understanding of the relevance of the day-to-day work can be helpful for motivating students to engage in it. And I also think for you, in terms of prioritization of experiments and things like that, if you think about the big picture of why you're doing it, it can help you identify whether is this worth doing right now or is this a more important experiment or something.
in that case, like I'll tailor my answer just a little bit. I think that in that case, like my broad body of work is still understand further validating this technique for that short time window. So that we can study the compliance of a fish fin in a short duration of time will continue to be my focus, more so than let's get these on robots and get them swimming. I think my work is I'm still inclined towards getting into the depth of this technique and getting it to work quantifiably and repeatably on a fish fin before I probably will think about putting fins on a robot. Not that I don't enjoy building robots, but
I don't mind doing the same part.
I don't either, but I do like building robots too, which is why, like, moving forward, I'm splitting up my time into still want to study this core scientific question of investigating compliance, of fish fins, but delving into just bio-inspired robots, not quite for just swimming, but for museums.
Right, and I'm not necessarily pushing you in a particular direction, just more that it's good to identify why you're doing something.
Right.
So that you can help others, either participate in the work effectively or give you effective feedback about it. Because you don't necessarily, like when we first talked about this, my initial were, we need to understand the underlying genetics happening in terms of, is it Because I'm a biologist and I'm a cell biologist, so I went there, right? But knowing that you're not thinking about that part means I can shut down that part of myself and focus on what you're actually trying to do.
Okay. Thank you. That's really good advice.
Congratulations.
Thank you.
Very impressive. So actually, I'm gonna be more speculative.
Sorry, what?
I'm gonna be more speculative. And the question for you is, mostly here you focus on the sort of constant, like Dr. Lau was saying, constant, you know, bulk mass properties, right? Okay. So we're saying sort of, I want to run some numbers from my own education. So which means that in your model, you actually are trying to pick one parameter from data.
Yes.
And so then if you're picking one parameter from data, for every, say for example, let's focus on the foil, because foil is here. So how many experimental files do you have?
So with the experiments with just the flexible foils that I did for the second milestone, we did 2 to 3 trials per foil. But for the parameter estimations, each vortex hit that plate that moved were 5 to 7 trials.
So now you have 5 to 7 calls, and basically, when you measure the reflection, that was still done by.
Yes, by visually tracking.
Was it automated or?
It wasn't. It was visually tracked.
Okay. So in theory, you could automate this process and be able to measure the reflection along the entire foil rather than.
Yes. So in the last couple months, I've done that on the plate. I haven't been successfully. So the software now I'm using is Canova, and it's working well on automating the tracking for the plate. It hasn't worked on the foil yet, and I'm working with like the markers and all that stuff. So we're currently working on that, but yeah, I can potentially automate that, and that will definitely improve the tracking, and we'll get better resolution, and hopefully we can see trends in a short period of time.
And so give me a sense of what if you. I'm trying to figure out how to formulate this question, right? So, how would you go about getting like better fidelity model, right? So, let me just put some context in. Right now, the big thing is data-driven, right? It's all about AI and machine learning, and if you sort of, really the robotics concept, I'm sure you've noticed it. Good growth is all machine learning, machine AI.
Whether people know how to apply it or not.
Right, exactly. We'll get that. We'll get to that. Right? So I guess the question from my perspective, right? So for a single parameter, right? I mean, this is effectively a regression problem, which existing AI techniques are super good at, right? So the question that I have is how difficult do you think it would be to effectively run through regression and be able to extract, how much more data do you want, collect in order for you to think that you will be able to get a good regression on extracting those parameters?
For the physical system or the fish?
Let's just start with the physical system. Because that's right?
I obviously haven't studied machine learning or AI as much. So let me just understand. So what we mean by the regression model is we're predicting something.
No, there's no prediction at this point. You're just doing model thing, right? It's a system identification problem. And you're basically, you have data, and you're trying to extract parameters.
Right.
What the model parameters are.
Okay.
Data, right?
So if I have the response of a system, like I've got these oscillations, the goal is, or the potential for using these models is that it will just look at the response and fit, but you still need that underlying model. So in my case, it was that single degree of freedom secondary system, right? I think for the physical system, it doesn't seem like it's going to be tough to do once I learn how to do it. But I've heard MATLAB has the capability of doing this very easily. I don't think for the physical system it's going to be tough because there is that underlying model I can begin with, right? Which is that lumped parameter single degree of freedom
So I guess
model.
what I'm trying to get at is literally take that long parameter model, the discretizer system, so that you actually have one, it's a sequence of long parameter models with constraints at segment points, right? And literally the machine learns this thing, assuming that the data is really up to date, you know, back, collected in a way. You could pretty quickly come up with a sort of multi-parameter model of, you know, reflected foil or plate, right? Different, you know, from the vortex.
So yeah, and I think like starting with, you know, the physical system, the plate on a foil is probably going to be the most reliable one where I could have tried this, you know, going on to maybe the foil, but you know, then the model does get more complicated. You can't really model the flexible foil as a lumped parameter system because.
But you can model the flexible foil as a sequence.
Yes, yeah. So I remember looking into using a model like the pseudo rigid body model, where you know each segment is attached with a spring, and then you're estimating those spring constants as the location changes. I mean, I definitely think that the tools are out there. I did not investigate those as part of the thesis, but the data from the physical system and the foil is very rich because it's controlled. It's much simpler than the data from the fish is what isn't as rich. It's,
So I
the limitation.
think that you actually have enough data as it is. Given the video data that you have, sort of put it out there, you can actually do a first step of how that is. As long as you can automate the process, extracting that after the day from your existing video. And I think the existing video is possibly.
I would love to talk to you more about them because with the existing videos, I wasn't able to get it to automatically track. I was only able to get it with the marker on it. So putting a marker on
Yeah,
it.
but that's because you're not doing the right thing.
I definitely wasn't doing that.
That was my comment. Okay. Based on the quality of the video, I just don't, you know, I don't know if the market is.
Okay. I definitely didn't think of even examining another algorithm for that.
I think you have a start of a really good example. And it's a very timely, it would be a very timely thing. Of course, a lot of these systems are just challenging with the data, right? A lot of these systems are large quantities of data. But there's actually, but the thing that the fact that you have a first principle model actually allows you to train the system that won't have data and sort of a lot of things are out there. So there's just things to think about.
Thank you.
Anybody else have questions?
George, Brooke? Just shaking their heads.
All right, well, great. With that,
You don't?
I'm your advisor. I don't get to bias people's view. I ask them hard or questions. So, Deeksha, thank you for you step out for a little bit and stay across the hall. We'll call you back in several hours. Oh, they can't see me. They can.
Did you turn on your video over there?
We're pulling the tape off the camera.
Okay, I can hear you.
You can hear me? Can you see me now? Oh, we're gonna.
No.
Don't mess anything up.
I'm still seeing Deeksha's slides.
Yeah.
Oh, there we go.
Hello.
I'll just say hi.
Hi. You want to stop recording or?
Oh, yeah.
Now we're off the record.
Okay.
Thanks, Steve. Elvis has left the building. Comments, concerns? Thank you very much both for being able to dial in. Thoughts? Push her forward, make her restart.
I think she needs a new advisor.
Yeah, he's the worst.
Yeah.
That was known early on, but you're at fault for not causing that to happen. So, any Jen, Annie, any concerns? Do we let her sweat, or is everybody comfortable with what she presented? And we.
Oh, I guess I have one last question. When is the final document?
I think it has to be in by Wednesday, and I have gotten through all the chapters and give it edits. So chapters, I think I may have these wrong, but 3, 4, and 5 were in decent shape. 6 and 7 needed I basically covered it in red. Those were really fast, quickly put together, and she has all my edits. But she does have to submit something on Wednesday to graduate technically this cycle. She's going to walk no matter what, and her job as long as she defends her job at Villanova is safe.
I'll have my edits to her by later tonight. I just wanted to wait in here so I wasn't asking redundant questions.
But so should we tell her that the defense went well? There's still people would like the final version, and anybody have any specific changes that are clear, or just wanted a cleaner edited version to sign off on?
Yes, please.
Yes, I think the cleaner version would be great. And I'm certainly fine signing any paperwork for the defense. She did a good job. I know it was a long haul, but the problem turned out to be very difficult.
Yeah. Yeah, it seems simple in that first, I remember, was it Timo?
Yeah.
Yes.
Designing the vortex maker, we're like, oh, this is going to be easy.
Yeah, Brooke and Timo and I just pushed something together. We thought, oh, no problem.
Yeah, and I have to say too, the mathematically, not even so much mathematically, but predicting the force of the vortex as it interacted with the flexible foil, that took a long time, right? And
Yeah.
working off of the models, off the rigid plate, and then verifying that the phenomena of the vortex didn't change very much and making that approximation, that took a while to resolve. But I think she did a nice job with that. But that certainly wasn't something that we should have. But I didn't anticipate that absence of information. And I don't think she talked about that. I think it would be nice for her to get that paper out.
Yeah.
Because that's a very different view. But if it's okay with you, I'll call her back in and tell her just that. Did well. We're happy to sign things. Want to see the final version of the thesis, and then she is good to go.
Yep, that sounds good.
Good. Well, thank you. I'll bring her right in. So I'll get over there. So I'll just try to represent the committee. Everybody thought you did very well. We're very pleased with how you brought everything together. Your body of work is fantastic. We are all happy to sign off and say congratulations. We all would like to see the final version of the thesis with all the edits made, and then we'll be very pleased to call you Doctor and Professor. So congratulations.
Thank you. Thank you.
Good job, Deeksha.
She says thanks, Brooke.
Thank you.
Thank you. Thank you all very much.
Thanks, Deeksha.
Thanks, George. Just quick admin stuff. They'll only send you the form for the defense.
Okay.
I'll send you all the dissertation form with the final draft.
Sounds good.
When does it due?
28.
Oh, the 28th, so it's not due Wednesday.
Oh, okay.
On Wednesday, so.
So you better get some. Where are you? Are you going anyplace fun?
Oh, I'm going down to Ocean City.
That's fun. All right.
Thank
Thanks,
you
George.
so much.
Thanks, Brooke.
Good
All
job.
right.
George, I'll see you in July. Brooke, we have to make plans to get together soon.
Absolutely. Absolutely. Definitely.
Good.
That sounds great, you all. Thanks, Deeksha. Congratulations.
Thank you so much.
All right, and Deeksha, we'll talk about experiments.
Yes, absolutely.
Talk to you later.
Bye.
Bye-bye.